Hello, myself Asutosh Kumar Mishra. I'm going to discuss here briefly solubility product and related solubility equilibria. So we talk about the solubility product in context of saturated solution of sparingly soluble salts. So the words are saturated solution of sparingly soluble salts. So first we need to become familiar with these two terms, the saturated solution and sparingly soluble salt. So to illustrate the saturated solution, I have taken here a glass tumbler and filled with water. To this, I'm adding the salt in some salt in small increments and stirring the solution using a glass rod so as to fasten the process of dissolution. So as I keep on adding more and more salt to this solution, stage there will come when no more salt can be dissolved into the solution. The solution is then said to be saturated with respect to the solute. So this is what about the saturation stage. Another term was there, sparingly soluble salt. So based on their solubility, the substances can be classified into the three major categories: the freely soluble, slightly soluble, and the sparingly soluble substances. So another new term we have got here, the solubility. Solubility refers to the quantity of some solute dissolved in given volume of the solution. Roughly, we may speak of, say, the molar concentration. So if the molar concentration or solubility has to be the 0.1, if it is 0.1 greater than 0.1, in fact, then the substance is said to be the freely soluble. The KCl, NaCl, these are the examples. Say the alkali metal salts generally are freely soluble. So there are sparingly soluble substances at other extreme. Their solubility is less, even lesser than 0.01 molar M. This is M means the molar concentration. Means only the 0. Even lesser than 0.01 mole of the substance per liter of the solution can be dissolved. So obviously these salts are very less soluble. In this category, we do have the AgCl, say the PbI2, say the Ag2CrO4 like this. In between these two extremes, we have the slightly soluble substances, and their solubility then will be lying there between our 0.1 and 0.01, like this. M means the molar concentrations. So when such a sparingly soluble salt is put in water, it dissolves only to a little extent, producing ions. The ions and the precipitate form or the solid form remains there in equilibrium. So here I have taken the case of Ag2S, the silver sulfide. So here we have the solid form Ag2S and the dissociated ions here also are. So how it dissociates is, I will be writing here through an equation, ionic equation. The solid Ag2S will be dissolving into the Ag plus, it will be dissolving and will be forming the aqueous Ag2S form. Aqueous. And now this will be dissociating into our Ag plus, 2Ag plus the sulfide ion. Okay, so we do have these dissociated ions. The problem with these salts are there with the solubility. Out of the given quantity, very less amount can be dissolved. Means Ag2S aqueous dissolution will be very less, but whatever amount will dissolve, that completely will dissociate, because Ag2S is salt and all the salts are strong electrolytes, so they will dissociate for sure to the 100%. But problem is there with the dissolution. So if I skip this one, then I may say that Ag2S remains there in equilibrium, in solid form remains in equilibrium with the dissociated ions, the 2Ag plus the H2 minus. Okay, so if we try writing the equilibrium constant, then equilibrium constant can be written as Ag plus raised to power 2 square in the S2 minus divided by the Ag2S concentration. So as we more often see that the substance is Ag2S type pure substances or the solid substances concentration is kept constant. So this has to be a constant. So we can cross multiply these two terms. So K multiplied with another constant is then will be called the KSP, and KSP will be then equal to the Ag plus concentration raised to power 2 and the H2 minus ion concentration. And to this I am putting now in a square box like this. So this becomes the general equation for the solubility product. To to be more general, I am taking a general salt, say the AX and BY. And now I'm allowing this to dissociate. I'm directly dealing here with the dissociated ions. So this will, how this will dissociate is XA and the Y plus and YB X minus. We are following the charge balance here in this equation. So if its solubility has to be the A's, then its solubility will be X's and its solubility is Ys, right? So if we try writing here the KSP here will be XS raised to power X, YS raised to power Y. So eventually this will come out to be the XX, Y raised to power Y and S raised to power X plus Y. So this becomes the general equation for our solubility product. So this is nothing but our equilibrium constant. And as we know that equilibrium constant is a function of temperature only. It will not be affected by change in concentrations. This is a function of temperature only. So as in chemistry, we often do use as per the IPC convention, the 25 degrees centigrade is the standard temperature for measurements. So at 25 degrees centigrade, the KSP values for a given sparingly soluble salt will remain constant. So here we have a table, and in this table, we do have many salts with their KSP values mentioned. These salts are hydroxides, carbonates, chromates, sulfate, oxalates, any type of substance can be here. And these substances will dissociate according to their ions availability, and corresponding KSP's values will remain constant. So how the questions are asked from this solubility product for the illustration, I am taking a case here. This is a question which has been asked in JEE. So this is our question. Question reads, if solubility product of Zr3PO4 is denoted by KSP and its molar solubility is denoted by S, then which of the following relation between S and KSP is correct? So, okay, to deal with this problem, I will be writing first here the equation for the dissociation. So we have the Zr3. I will have to use larger pen size. Zr3PO4. Just a minute. Zr3PO4 all 4. So how this will dissociate? This will dissociate into the 3 zirconium Zr4 plus ion plus 4PO4 3 minus ions, right? Like this. So if its solubility has to be the S, then its solubility is 3S and its solubility is 4S. So if we try writing the KSP here, the KSP values will be 3S raised to power 3 and 4S raised to power 4. So this is 27S raised to power 3 cubic power, and 4 4s are 256S raised to power 4. So this is our KSP value. When we multiply these two terms, this comes out to be the 6912 A's raised to power 7, and this is our KSP value. So how the A's will be related, we eventually can see that this relates to our option B. So this will be the answer. Then there happens to be the cases of simultaneous solubility. So to illustrate the simultaneous solubility, I have taken here another case. The question has been asked in JEE Advanced 2013. The KSP of Ag2CrO4 is 1.1 into 10 to the power minus 12 at 298 Kelvin. The solubility in mole per liter of Ag2CrO4 in 0.1 m AgNO3 solution is. So basically, I will be writing here the dissociation equilibria for our sparingly soluble salt, and this is Ag2CrO4. Ag2CrO4. So Ag2CrO4 will be giving the two Ag plus ions and the CrO4 2 minus ions. Simultaneously, there is AgNO3, and this is a strong electrolyte. So this will be dissociating, this will be giving the Ag plus and the NO3 minus ions. So Ag plus will be coming out from the two sources, one being the sparingly soluble salt Ag2CrO4, other one being the AgNO3, which concentration has been given 0.1. So this will avail us the 0.1 m concentration of the Ag plus. Say the solubility of Ag2CrO4 has to be the S, then its solubility will be 2S, and it's also the S. So when we have some dissociated ion in solution from two different sources, then equilibrium never knows that where from it is coming. So KSP value, however, will remain constant because this is an equilibrium constant, and this will be Ag plus concentration into the CrO4 2 minus concentration. Ag plus concentration will be h to the power 2. So Ag plus concentration is 0.1 plus 2s raised to power 2, and the CrO4, this is S. So KSP value is given here, and KSP value is 1.1 into 10 to the power minus 12. So compared to 0.1, this value is going to be negligible. So I'm keeping this 0. So 0.1 C square is 0.01 into S has to be 1.1 into 10 to the power minus 12. So S will be equal to 1.1 into 10 to the power minus 10. So this matches here with the option B again. This then becomes the answer. So this way, the solubility equilibria problems are solved. So this solubility product, and there can be other cases of simultaneous solubility. Say we have the AgBr and the AgCN, GSCN type of the sparingly soluble salts. But I think then the video will become more larger as I have to restrict it to the 10 minutes. So then there are many applications even for the solubility equilibria, like the salting out of the salt and also in the qualitative analysis. So keeping in mind the time limit, I will be ending here the video. Thank you.